show me where to go, roughly. Now hold on, one more time. Did we really like doing that one?
Not really.
Oh. Compared to that one?
Oh, yeah.
Okay, so we like that one more, right?
Yeah.
But what was the problem? What was better in this one than in that one?
You can see the flow. It's easier to visualize.
It's easier to visualize when you have more points. Anyway, just a heads up, moving on. Here we go. Okay, so when we look at a slope field from a, oh no, it's 6 minutes, 7 minutes. Okay, so when we look at a slope field, we are looking at a flow as shown by slopes of differential equations. From differential equations, I shouldn't say of, because that would be the second, and never mind. Example number 5. Cool kids, it should be easy. What is the one general original equation that could fit that flow? Which one? LN. Some of you are like, how do you know? I don't know. I'm just picking a random and I'm saying follow the flow, and then you're like, hey, look, he's in. Are we good? Okay. Y equals are fairly easy. Hold on. Can we look at this page real quick? Some of you might still need to write some things down. Where do these types of questions fall under these possible types of problems? Which one would be a classification of the two that we just did, example number 4 and example number 5? Given slope field. Okay, given slope field, we're down to here, right?
Yeah.
Which one?
Y equals.
Choose y equals, right?
Yeah.
So these are technically examples 4 and 5, just so we can kind of fit them in. And then how could you explain to someone else maybe a hint or a clue or a process or a way of thinking in order to match a slope field to an original equation? What would you say? How would you explain it? Let's say you're the teacher or the tutor. You make some good money in college if you tutor calculus. Anyway, come back. No, seriously. And then even after. How could you explain matching a slope field to an original function? What would you tell them to look for or look at or think through? Here, I'll just write it. Okay, hold on. Write them. Then we'll fill in some clues. Please maybe give me, like, skip a line if you can. If not, there should be room next to what you wrote because you guys have long lines. My portal smartboard has short lines. If you can, or you can write it next to. I'm sorry. Do what you can, bud. Couple more seconds. We should be getting close, and some of you have already dropped your pencils, or you're just like kind of staring in space, and I hope you had a question. How would you explain? How would you give hints or tricks or clues for how to match a slope field to an original function?
Follow.
Graph? I heard graph, I heard follow. Follow the graph? Hey, that sounds good. Follow the flow?
Follow the flow up the graph.
I don't know. Not exactly sure. I think I said something this morning about fit a function in the flow. Is that what I said? Fit to the flow? I don't know. You can follow the flow, you can fit to the flow. The original function is a function that moves through the slope field. So basically, if you follow the flow, you'll know y's behavior. And hopefully, like in these, you know generally what these or how these behave, right? So you can fit to the flow. All right, question. This one's going to be really hard. It's going to be harder. This one's going to be really hard. It's going to be harder. Let's go back to number 2 real quick. Number 2, you're given what? A solution. So they give you one equation, like, I don't know, y equals
Let's put x squared plus
x squared minus y squared all over e to the x. Oh, that would be mean. Anyway, and they say, hey, match it to a slope field. What do you want to do? If you can, analyze the function's behavior, right?
Yeah.
And then go looking looks like what?
I said B looks like
B looks like.
X.
Okay, hold on. Give me one. I just got like little pieces of 5. Give me one.
B looks like X squared.
B looks like X squared.
We don't know more.
Wait. Pause. What are you looking for?
Oh.
What's different? What's different? What's different? They're not y equals. What are they?
DY.
Bummer. However, hold on. If y equals x squared, do I know how to find dy dx?
Yeah.
I hope so.
Yeah, I hope so. So if I see, here's one method. One method is, you know what? I think I know what he looks like, and he looks like, so if he's this, then I'm guessing that he is something linear. Wait, is there something linear?
Yeah, X.
Hey. So I can say maybe 4 is B? Hold on. Is there maybe a better way of thinking about this? Anybody? Because you just said that looks like x squared. I'm not saying it couldn't have been. I'm just saying, could you have maybe have integrated dy dx equals x and multiplied and said, hey, the integral of x is x squared over 2? Maybe a little more precise. And then say x squared over 2 is a parabola, and which one's parabolic? B. What's another one that you could do with a similar or in a similar fashion? D? What about D? Sine? Are you sure? Why? Hold on, that doesn't look like a sine. That doesn't even look like a cosine. That looks like an upside down cosine. A negative cosine? Wait a minute. What do I know about? So many light bulbs just went ding. Okay. If I look at this graph and if I follow the flow, some of you are like, how am I choosing it? I'm just choosing one and going for it. If I follow the flow, it looks a lot like a trigonometric function, right? And more specifically, sine or cosine. And since it's starting at, not the middle, but like the lower, hey, that's a cosine, but he's been flipped. Wait a minute. Who is cosine? That would be my original function, right? Hold on. Who is cosine the antiderivative of? But the antiderivative of sine is negative cosine. True?
True.
Is there one more that we could do with it in a similar fashion? F? What about F? Hey, he's nice because, question. What's the antiderivative of e to the x? So kiddos, here's one thing that we can think about with, let's go back real quick. We're being given slope fields and we're trying to find what? Differential equations, right?
Yeah.
We could, I'm going to say consider, if possible, oh dear, the antiderivatives. Why do I say if possible? Well, we already talked about how one of those in the A, B, C, D, E, sorry, 1, 2, 3, 4, 5, 6, how one of them we cannot integrate. And actually, it can't be integrated at all. It just can be approximated by an infinite Taylor polynomial series. That's Calc 2. But sometimes we can consider antiderivatives, and if we can consider antiderivatives, then we can say, hey, what's your antiderivative? A parabola! Yay! Right? We can fit the flow. Here's a dilemma. We have 3, and maybe some of you are like, you know what? I can kind of think through. I know you can kind of think through maybe 1 or 2 of these, but pause. Hold on. They like to give you ones that you can't necessarily always think through and antiderive. So what can we do? Question. If we're looking at, hold on, what have we used so far? We've used D, we've used F, and we've used B, right? Okay. We have A and E and C. Are there any special slopes that you can see in A or E or C? E has what? The linear line? Like this one?
Yeah.
That's a good one, but I like this one better. Why do I like this one better? What's true if they're flat? My dy dx is 0. Horizontal tangent line, my derivative is 0. So if I know my derivative is 0, hold on. Dy dx equals 0 when, Are there any other special ones in A or C?
Yeah.
Yeah, what? A. A has dy dx equals 0 when, How about C? Does he have any flat ones? Follow the flow. If you follow just those few special slopes. Question, can we pull out which one's which? Mm-hmm. Because, couple things. First of all, question, what is this line? What is this function? X equals 0. When x equals 0, dy dx has to equal 0 because x equals 0 is this line, right? I'm not saying the line is a part of the slope field. I'm just saying that line has all zeros of derivatives. Question, what's this line? Y equals 0. So when y equals 0, all the slopes are undefined. Question, which one has, if x is 0, it's 0, and if y is 0, it's undefined? 2. Think about it. If x is 0, the slope is 0. If y is 0, the slope is undefined. And then if x and y are 0, indeterminate, what is that? Anyway, question for another day. C. All right, we have 2 more left. Can anybody give me an explanation as to why, which one is which?
Oh, okay.
Nick. A is 3. Good. Why?
When y equals 2.
Nice. Now, do you necessarily know exactly where these little tick marks are happening? No, but you do know that it's y equals something, right? Y equals some positive number. What's the only positive number I see? 2. Hey, does that make sense? Y equals 2? Yep, on y equals 2, if I plug in 2, everything's going to be 0. Everything. Sorry, apologies. The slope will be 0. No ambiguity, right?
Right.
Okay, so fine. We know the final answer is E, but why? No, okay, yes, that is a valid strategy. Process of elimination, but why? What would make this 0 when the y equals the x? And what line is y equals x? Oh, right? 1, 1, 2, 2, 3, 3, field, there we go. If the field of slopes. Anyway, never mind. The dy dx is equal to 0, right? And then if it looks this way, I'm being ambiguous because my words are not working today, it's over 0. There we go. Here, hold on. I'm going to do this. Okay, there we go. Do we get it? They're like up and down and they're horizontal and vertical. They, the slopes in the field. I'm done. Okay, come back. Hey guys, slopes along the x-axis. Didn't we have something? Okay, it wasn't along the x-axis. Oh no, it was. Hey, what was I talking about? If it's along the x-axis, what do I know is true along the x-axis? Y equals 0. So, if I have slopes that are along the x-axis following a certain pattern, I know that all of those along the x-axis are when y equals 0, right? Yes, I know you should know that, but for some reason we just, I don't know. It just, algebra 1, it's gone. Okay, slopes along the y-axis. X equals 0, right?
Yeah.
So we can go to our dy dx. Hey, remember, every time I say slope, dy dx is equal to a numeric value, or it gets out numeric values of slopes. Okay. Slopes only dependent on x. Let's fill in these clues, but you might not necessarily understand them right away. We might have to see some examples. But I'm going to say same slopes horizontally. No. Vertically, I apologize. I'm going to put an ambiguous x equals a because I can't tell you exactly what x is going to be. But for all the x equals 1, x equals 2, x equals 3, those are all vertical lines. And along those vertical lines, if the dy dx only has x's, well, all those on the vertical line will be the same. And if it's only dependent on y, then I'm going to have same slopes horizontally. The little munchkins are coming. Same slopes horizontally. Along, if it's only dependent on y, that means it only takes a y value to plug in. Therefore, if I know one set y value, which is along a horizontal line, then any of those points I plug in with the same y will have the same slope. Where slopes are positive or negative, this is what we haven't really used as a clue yet. Well, we didn't really use those. We kind of did. Where slopes are positive or negative. Guys, slopes are positive. We can tell because the slopes in the fields of the itty-bitty tangent lines are going to be up, right?
Yeah.
And then if it's negative, they're going to be down. Okay. We can consider test points and the resulting, like when you choose a test point, when you plug it into the dy dx and the resulting signs of dy dx, hence the signs of the slopes. That might not make sense yet, but we'll look at it. Technically, to be honest, those are pretty much like my entire arsenal of clues for looking at slope fields. That's not a no-no, because I think it's enough. I don't know. I'll think about it. I don't think there's really any more I'd use besides considering the antiderivative, right? We already wrote that down, didn't we? Did we say consider the antiderivative?
Yeah, where possible.
Yeah, if possible, consider the antiderivatives.
Nah, that's good.
Okay. Zoom. Ready? Okay. 2 more seconds.
I'm ready. You can go on.
Maybe 5.
It's online. It's online.
Okay, we good? But you should. Okay. Example number 7. How much you guys take a second? Just kidding. Take a minute. Take 2. Number 7, go. I looked at the clock and I was like, oh. I want you to try to match every single one. Nice thing is, all of them are used, and none of them are used twice. Hopefully we know that, though. plug in x is 0, then it's going to have a slope of a negative. And you could keep on with that logic and say, hey, when x is 2 times 1/2, hey, that could have slopes of zeros. Anyway, that works. Okay, Jezreel, what were you? We want to do another one?
Yep.
Okay, go.
I think that D and 4 are the it.
D and 4 or B and 4?
D and 4.
You already asked me that. My telling look. Okay.
I thought that was like a backwards.
Number 4 is A. Why?
Because if you look at like the horizontal line.
Okay, so we're looking at these ones, right?
Yeah. When x is -1, y is +1, and so the derivative is 0. Yeah.
Let's check it. So when x is -1 and y is +1, or similarly, if x is +1, y is -1, can anybody give me a general? This is when dy dx's were 0, right? Can anybody give me a general what this kind of looks like? Y equals negative x, and whenever y is equal to negative x or something thereabouts, if I plug it in, hey, zeros, nice. Therefore, 4 went with A. Another one. 2 is C. Why? Ooh. Dai, you're going for it. She said when you solve for the antiderivative. Now some of you are like, ew. But if you solve for the antiderivative, you do end up with an ln. However, hold on, keep going through that with me because that doesn't look like ln, right? What else would you have to do, Dai? Solve for x? Solve for y, and so then you're going to have some sort of y equals an exponential, right? However, a slight dilemma. Wait a minute, why is it above and below? Because c's can be positive or negative, and when you have positive c's, it's an upward e, and when you have negative c's, it's a downward e. But does anybody have another way that didn't make you integrate? I'll give you one. Jezreel, shush. Does anybody have another way that didn't make you take the antiderivative? Lord Calvin. Yeah, totally.
Well, the slope only depends on y, so that means that it's going to have the same slopes horizontally.
Same slopes horizontally. Jezreel, are they the same slopes as you go across? Like all of these are the same horizontal, same horizontal?
It looks like it.
Yeah. So dependent on y's, that would be another one. And you're like, hey, this has to be the same across, no, same across, no. Hey, the only option is, technically, does anybody have one other way? Nick? Oh, you're going for the last one? Hold on. Anybody have another one? Nobody? Where were the horizontal tangents? When y equals? When y equals 0, does dy dx equal 0?
Yeah.
All right, fine. Nick, the last one.
Well, it equals D.
Okay, it's good. Why?
Process of elimination.
Okay, that is a valid technique. I will even give you a dum-dum. But someone else tell me why. That sounded weird. Sorry. Tell me why. Just why?
Because if you take the antiderivative, you'll get some squares, and that makes it look like a circle.
Okay, for a dum-dum, you're totally right, and actually that's a good procedure. But question, how would you have to rearrange this to find the derivative? Or to take the integral?
You have to take dy over y. Oh, dy times y, and then negative x times dx.
And when you take the integral of both sides, I agree, squared squareds. And when you have squared squareds, he's a negative. Hey, Adam, he's a squared plus a squared. That will be a circle. Okay, that's good, and that does work. Does somebody have another way? Josh. Hold on. If you look at the graph, good start. When x equals 0, that's going to be the vertical line, right? When x equals 0, what happens to my slopes? 0. When y equals 0, are we going? Sorry, Josh.
Yeah.
When y equals 0, what's going to happen? Draw your circle and say, hey, where are my horizontals? Oh, there they are. Where are my verticals? Oh, there they are, right? So when y equals 0, undefined. When x equals 0, horizontal. Good. Nicely done. Kiddos, example number 8. Sorry, example number 8. Does guys were bored and looked ahead? What do we do for 8? Okay, does this necessarily fit into one of my, not necessarily, but which statement is true for all solutions of, all solutions of? All solutions of? For x greater than 0, what parts of the graph am I looking at? Where's x equal 0? Please tell me. The y-axis. So x greater than 0 goes? Okay, so quadrants 1 and 4. And quadrants 1 and 4 are all solutions decreasing. What's going on in quadrant 1? That doesn't work. Number 2, all solutions level off near the x-axis.
Yeah.
Number 3, for y greater than 0, what quadrants? Come on. 1 and 2. For y greater than 0, which is quadrants 1 and 2, all solutions are increasing.
Yeah.
Good. So therefore, my final answer would be? Keep going. Example number 9. Ooh. Man, they're testing me in different ways now. Vertical segments. What does it take to be to have vertical segments? Segments. Huh? dy dx, I heard it in the back. Over 0. Dy dx will be over 0, right? So what am I going to do in my problem? Yep, set the denominator equal to 0. And when you solve, you get, well, hold on. I'll throw it in. What are we solving for? Look at all your answers. Help me out. Y equals what?
Oh, negative. Yeah, negative.
Therefore, final answer is? Good. Example number 10. Which statement is true about the solutions? Y of x of a differential equation whose slope field is drawn at the... Alright, hold on. Can you even tell where the axes are? Do you see them?
Yeah.
Careful.
Wait, maybe.
Careful. Look at yours. It's better than mine. Okay. So we have the -1, -2, 1, 2. Okay, we see the axes. If y of 0 is greater than 0... What? Did they just give me a point?
Yeah.
Okay. So if y of 0 is greater than 0... So at the point 0, 0, the y is a little bit positive, or somewhat positive. Then the limit as x goes to infinity, the limit as x goes to infinity of y of x is approximately 0.
Yeah. Wait, what's that?
If y of 0 is greater than 0. If y of 0 is in between -2 and 0, if y of 0 is less than, holy cow, what am I looking at for every single one? Okay, hold on. What are they talking about? Y of 0. Right here, right? They're telling me, because, why are they telling me? Because I can't see exactly there, right? There aren't there aren't segments on y equals 0, true? At all. However, could we kind of see somewhat some behavior going on, right? Does it kind of seem like there's some sort of, wait, what? Wait, hold on. Okay, so there's weirdness going on, right? Which is why they give us all these different conditions and say, hey, so, that little guy right there, if he's positive, then what's going on? If he's positive, is that going to be a horizontal tangent line? Wait, why did it say horizontal tangent line? What's it mean if the limit as x goes to infinity? Hold on. If x goes to infinity, which direction am I going? To the right or to the left? Wait, what? Where's x going if I'm going to infinity? Where are the y's going if I'm going to infinity? Is this a bad question? Hold on. Give me a second. Aren't question. Let's just work through in the next 90 seconds. If we would know what to do, just because it's good practice, I'll come back, peek at number 10, and maybe write in some stuff if you want to look online over the weekend. Kiddos. Sorry, actual example 10. Consider the differential equation. Okay. Sketch a slope field. What would you do?
Table.
Make a table and then put it in. Would you necessarily have to put every single point in the table? No, but put enough and be really particular when you get here. If it's positive, it better be sloped up. If it's negative, it better be sloped down. If it's horizontal, it better be flat. If it's vertical, it better be vertical. Anyway. B. Let f be the function that satisfies the given. Oh, wait, they might put a slope field together with solving a differential equation. Write an equation for the tangent line. Oh, never mind. That's not an original yet. Tangent line. How do I do tangent line? We had something recently where I realized we're starting to forget. How do we do tangent? Y minus equals n times x minus x1. We get the x1 from, hopefully then, the y1 from, well, hopefully we'll figure it out. And then, oh yeah, hey look, how do I get m? F prime of x1, which would be the same thing as dy dx, such that x equals negative 1, right? Or sorry, x equals x1.
Yeah.
Part C, find a particular solution. What would you do? Times dx, right? Divide by y, right? I would actually solve, right? And then D,